This is video 1 for the electricity and magnetism unit. So your learning goals for this unit, I want you to be able to discuss electricity. That means current, resistance, voltage, and power. I want you to be able to explain why fuses are important. For your math learning goal, I want you to be able to solve problems involving electrical power. Then I want you to be able to discuss the differences between permanent, temporary, and electromagnets, and then discuss the Curie temperature and how that affects magnetism. So let's get started. Electricity. This usually is the movement of electrons. These tiny particles are about 1/2000th of the mass of an atom, but they can exert some huge forces. We call these electric forces. And these forces are exerted on other electrons or other protons. Now, if you take 2 electrons and place them 1 centimeter apart from each other, there will be 2 forces acting between them. A gravitational force that's pulling them together, and an electric force that's repelling them. So let's calculate and compare. So first, the electric force. The way we calculate electric forces is we take something called Coulomb's constant, and then the product of the 2 charges divided by the distance between them squared. Coulomb's constant is 9 billion. The charge of an electron is 1.6 times 10 to the negative 19th. And then 1 centimeter is 0.01. And then we got to square that. And when we multiply these numbers and divide it, we get 2.3 times 10 to the negative 24th newtons. So there's a force of 2.3 times 10 to the negative 24th newtons pushing these electrons apart. Now let's calculate the gravitational force pulling them together. Mathematically, the 2 models are very, very similar. We got a constant times the product of the 2 masses divided by the distance between them squared. So capital G at 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. The mass of an electron is 9.1 times 10 to the negative 30, negative 31. The distance between them is a centimeter. Square that. And then when we calculate this, we get 5.5 times 10 to the negative 67th newtons. So then, comparing these 2 numbers, obviously one's bigger than the other. And we see that the electric force is 4.2 times 10 to the 42 times greater than the gravitational force. Electric forces are the second strongest forces in nature, while gravitational forces are the weakest forces in nature. And hopefully this math, I know it's a little lengthy, but hopefully this math helps to illustrate how much stronger the electric force is than the gravitational force. So then, let's get a little further in depth here. Electric charges. This is the property of an electron that gives its force, and it has a name. The electric charge. The charge of an electron, I mentioned before, is 1.6 times 10 to the negative 19th coulombs. So the charge of the electron and proton are exactly the same. So the proton has a charge. So if I said the charge, we use a Q for charge, of the proton will be positive 1.6 times 10 to the negative 19th, while the charge of an electron is negative 1.67, or 1.6. And these are coulombs. So if we combine an electron with a proton, that gives us our hydrogen atom, and then the total charge would be 0 because the two charges will cancel out. So this hydrogen atom does not feel an electric force from other particles. It's now neutral. Since the force on the proton and the force on the electron are opposite, they cancel each other out. So we say that the hydrogen atom is neutral. Neutrons also have a mass that's similar to a proton, but the neutrons have a charge of 0. Now, the reason why comes from something called quarks. Now, there are 6 different types of quarks. Up, down, strange, charm, top, bottom. Of these quarks, up and down are the important ones. Those are the quarks that make up protons and neutrons. So the up quark has a charge of positive 2/3 the elementary charge. And the elementary charge is 1.6 times 10 to the negative 19th coulombs. So up has a charge of positive 2/3, 1.6 times 10 to the negative 19th. Down has a charge of negative 1/3 the elementary charge. So negative 1/3 of 1.6 times 10 to the negative 19th. Now a proton then is made up of 2 ups and 1 down. So if I take a look at the charges, that's going to be positive 2/3 plus 2/3 minus 1/3. And if you can do that math real quick, you find that that is a charge of positive 1e, or 1 elementary charge, or positive 1.6 times 10 to the negative 19th. A neutron is made up of 1 up and 2 downs. So that's positive 2/3 minus 1/3 minus 1/3, which equals 0 elementary charges. So the reason why protons are positive is because of their quark configuration, and the reason why neutrons are neutral is because of their quark configuration. Charge itself is quantized. So as far as we know, all charges in nature are exact multiples of the quark charge. So this is stated in physics by saying that charge is quantized. Particles can have a charge of either negative 1/3, positive 1/3, 1, 2, or etc. That's how 2/3 works as well. However, we cannot have a charge of 1/2, 4/5, or 1.22 of that elementary charge. So all charges are multiples of either 1/3 or 2/3. So you might guess that the reason is that all particles are made of quarks, and that's a very reasonable assumption. However, electrons are not made of quarks. So there are a whole bunch of particles out there that, some are pretty exotic. The new theory is that all particles are made up of objects called strings. So if this theory is true, then the reason behind quantization is simple. It's that all particles are really made of the same kind of stuff. So that's getting a little deep. So let's bring it back a little bit. Let's talk about electric current, or the amps. So if you were to take a battery and take a wire and connect the positive end and the negative end, what's going to happen is that electrons are going to flow from the negative end towards the positive end. And this is because opposite charges attract and like charges repel. So the electrons are being pushed away from the negative side of the battery and are being attracted to the positive side of the battery. So when charged particles move, we call this electrical current. And we use water current as an analogy. So for water, we can measure current in gallons per second. For electric current, we measure it in terms of electrons per second. So a practical unit then is something called the ampere, or the amp for short. And what an amp equals is 6 times 10 to the 18 electrons per second. So that's what an amp is. So the current that flows through a light bulb is typically around 1 amp. Wires in your house can carry up to about 15 amps. Now, if you have multiple things plugged into an outlet, this 15 amps is divided among all of those systems that use electricity. 1 bolt of lightning contains thousands of amps. Now, the way we move this electric current around is through wires. We can think of wires like a pipe for electrons, kind of like how water is carried through pipes. So from chemistry, I want you to remember the atoms of metal are held together with metallic bonds. And this type of chemical bond allows some of the valence electrons to travel freely through the metal, going from one metal ion to another. Those free electrons sometimes are called the sea of electrons. And you've probably also noticed that most electrical cords have 2 wires in them. The second one is for the electrons to return. And this becomes important for designing safe circuits. So generally, if you are to get shocked, what you're doing is you are completing a circuit. So if I take a look at this example right here, this bird is not getting shocked because that bird is not completing a circuit. Sure, the bird is touching a wire, but there's nothing connecting the bird to the negative side of the power supply. When you look at a power supply, we see long and short lines. The long lines represent positive, the short lines represent negative. So this bird is touching the wire, but there's nothing connecting the bird to the negative side of this power supply. This person is touching the wire, but the person's also touching the ground. The negative side of this power supply has also been connected to the ground. That provides a path for the electricity to travel through the person and back to the ground or the negative side of the power supply, so that person will get shocked. If I take a look at this next example right here, here we see a bird that's safe because it's only touching one wire, and here we see an unfortunate bird because that bird is connecting two wires. Um, Generally, when we see these two wires, electricity might be flowing one way through one wire and another way through a different wire. We'll talk briefly about how houses are wired so that we can figure that out. But that bird's providing a path. Sometimes you see squirrels doing the same thing. For those of you who farm, you may use an electric fence to keep in your livestock. Generally, what this is we have one line connected to the wires, and then we ground the other side. So, if you touch the wire, you are completing a circuit because you are touching the ground, so the electrons can travel through the ground and back to that power supply for the electric fencer. So, something else you may notice, mechanics, when they install a car battery, they are very careful not to touch the metal part of the car. And that's because generally the electronics in a car are grounded to the metal body of the car. A car battery itself can deliver up to 100 amps, and that's quite a lot. All right, we're going to conclude the first video here. We'll pick up in the next video talking about resistance.